I hope the title of this talk was intriguing enough for most of you. I think I did a good job, like most people that I met in the, at lunch were like, what do you mean? All right, so let's talk about what we do at my company. So I work at Boozt, which is a company in Sweden, is the largest, probably, online department store in the Nordics. We're over 1,000 colleagues from 38 different nationalities. We have offices in Europe, 7 offices, and we're over 150 developers. And internally, I'm building a payment gateway for like the internal consumption of Boozt and maybe selling it to other merchants. So back to our title, an entire payment gateway in a database. The first thing that comes to mind to most people that I find is, yeah, but why? Right? Or like as yesterday, I also got multiple times, that sounds like a bad idea. So let's see. I need to answer this question from 2 angles, this why. So the first one is the need for a new payment gateway. Why would you build this at all? So a payment gateway is actually something quite complex. Like the entire journey of a payment is quite long. So it starts with the customer pays at a store, the store communicates with the payment gateway, the payment gateway calls a payment processor, which calls an acquirer, is a company that is allowed by a license and some regulation to talk to the card scheme, for example, Visa and MasterCard. And then finally, the scheme will withdraw money from the bank will send it to the acquiring bank, which is the bank of the merchant, and finally, back to the store. You can see it's quite a long journey for the money to reach back to the merchant. And what we call a payment service provider is the combination of a gateway and a payment processor. And we're aiming to be one of those. We're aiming to be one PSP. So you can see the journey is quite long. And this answers the first question. The more intermediaries we have, the more problems we have. And with each intermediary, we have fees, like Ticketmaster. And if you can manage to cut some of the intermediaries, you can actually negotiate better prices with the acquirers. Problem is that Boozt has tried to do this in the past, but having a contract with different acquirers is a lengthy process and a negotiation process. So this takes time. And finally, the last problem we had is that certain payment providers actually are trying to compete with Boozt in the same space. So they try to get the customers from us and sell their stuff to our customers. So hence the need for a new payment gateway that we can control. So when I got this task, I went into planning phase. So I tried to break down how I would implement the payment journey as a simple system. And it looks like this. So you first create an idempotency key to prevent duplicate payments. You create the payment request. You charge the customer in the payment processor. You update the status in your database or whatever you have. Then you store some audit information for the finance people. And finally, you notify the merchant back that the payment was done. Okay, simple enough. It's a bunch of steps, but nothing too tricky. The problem is that each of these steps can fail. Okay, and that's bad because you don't want to charge the customer twice and you don't want to lose the money. So we know the solution to this. Like this has been studied over and over. The solution is basically introducing transactions. Simple enough. So I have drawn 3 transactions that need to happen. At the end of transaction 1, I have created the payment request. At the end of transaction 2, I have stored the audit information. And finally, the 3rd transaction is just to notify the merchant. But there is a problem in my design. This would work fantastically if it was everything in my system. But I have identified that there are 2 external databases that I need to communicate with. And if you have ever dealt with the idea of synchronizing 2 databases, you know this is not a trivial problem, right? Because you need to make sure that the state in one system is exactly the same as in your system. That's actually a topic of research. It's not something simple. So we need to say it out loud, like these 2 are not really atomic. They don't belong in a transaction. So that's a problem. So the next idea is that I could model this as state changes, because if I can model it as state changes, then I can apply different transaction ideas to these states. So I have identified 3 states: payment created, charge created, and then I'm done. And then we have our 2 foreign state changes, and at least the 3rd one happens in its own transaction. I need to do something about the first state change. So what I want you to notice is that there are 2 arrows going up, and they line perfectly with the start of a foreign state change. That is not a coincidence. And I think there might be an insight right here. I don't think it's a coincidence that the 2 transitions from one state to another are actually at the start of the foreign state changes. So I have 2 insights. One is that the transaction flow of a payment is directed by data changes. Okay? So this is not just procedural code. This is not just a simple system. It's something that is directed by how the data has changed over time. And the second insight is that I should absolutely minimize foreign state changes. Why? Because the more foreign state changes that I have, the more arrows going up I have, meaning I have more states, meaning I need more transactions and more retries and so on. It's more complex. Complex. I don't want complexity, right? Who wants a complex system? We all strive to have simplicity in our systems. So I'm going to take you to a quick detour to get out of the tar pit. Okay, out of the tar pit was a paper published in 2006. It's a quite long paper. It's a really good one if you want to check it out. I guarantee it's worth your time. It's going to take a while to read. So I'm going to do a TLDR for you. This is what the paper says. The paper says that complexity can be tamed by identifying the main sources of its complexity. And it identifies 3 sources: state, control, and code volume. And for each of these offenders or sources of complexity, it identifies the biggest of those problems. So for state is mutable state. We all know that mutable state is problematic. For control is explicit concurrency. So trying to do your own threading system, communicating data from one thread to the other is a source of complexity. And for code volume, which is something you cannot do anything about, like the more features you have, the more code you have, the problem is not the code itself, is that your code has too much power. So there are too many places where things can go wrong. So the solution for each of these offenders is, for mutable state, is reduce as much as possible. For explicit concurrency is ban outright explicit concurrency. And for too much power is to restrict the power of what developers can do. So it has these recommendations. Data should be handled using relational algebra. So this would reduce the mutable state. You should use a restrictive language. You should prefer domain-specific languages. And you should let another system handle the concurrency for you. I'm not sure if this sounds like any system that you know. Like, does it sound like any software you've heard about? Well, to me, it's exactly what a relational database does. It just ticks all of those boxes, right? So combined with the other two insights, for me it was clear that if I wanted a simple system, I needed to handle as much state in the database as possible. So let's talk about state in the database. Let's go back to, we got out of the chart pit. Remember this? We have our foreign state changes. We have our 3 transactions. We have some states. This looks like a state machine, doesn't it? So can we transform this somehow into a state machine and make it live into the database? So I have transformed it a bit more into a state machine. It looks like we have an initialized state, processing charge created, and then done. I have broken things a bit more, so now we have 4 transactions instead of 3. The key idea is that foreign state changes live inside their own transaction. They're not touching anything else. Okay, so now I have arrows for every transaction that I have. So I need a state for every transaction. And then how do I move from one state to the other? I do events. So I notify payment created in this arrow, and then it triggers a job. So it stores the charge job. Then this notifies charge created. Then I notify payment done, which creates another job, which is to notify the merchant. And finally, I notify the merchant, and the payment is done. So here at the bottom, we have the states. The blue lines are transitions, and the yellow lines are just events. That's the main idea of a state machine. So how do we handle state machines in the database? That sounds like a crazy idea. So there is this other paper that I can really recommend. It's called statecharts, a visual formalism for complex systems. And statecharts are a way of creating state machines that are visually representable, that are composed of smaller state machines, and that they form a hierarchy of state machines. So you can draw them out of tinier pieces. So composability is actually a good thing. So I'm going to give you a crash course into statecharts. All right? So statecharts look something like this. There are regions in the statecharts, there are boxes that include smaller state machines inside. And then entering these regions activate substates. And then actions cause transitions. You can move from one state to another thanks to an action. And then entering a state may trigger an event. So for example, in here, you can go from working back to idle, and then the action is to reclaim a connection. Okay? And also leaving a state may also trigger an event. So this is the basic idea. You have states, you have transitions, you have actions, but you also have ways of triggering stuff. So I'm going to show you how a real state machine may look like using state charts. This is a real example. It's not very readable, but it doesn't really matter. You can see the boxes grouping states and lines going everywhere. And then inside of those boxes, there are triggers, actions that every time I enter this state, this should be created or activated. And then you see in the editor an XML. And that XML is actually a standard by W3C. It's called SCXML. It's very well specified, so that's why we adopted it. And then we wrote a program that transforms the state chart into SQL. All right, so basically what we did is we wrote an interpreter of state charts in SQL. How cool is that, right? So this simplifies development a lot. Like, you have no idea. Like, you can draw your entire process of a payment, which is quite complex. You can discuss it with stakeholders. You can agree on it. You can publish it as documentation, and then you can transform it into interpretable code inside the database. So it actually creates an API. The API is just 3 functions. The first one is creating a state chart with the latest version. The second one is to start a machine based on a machine ID. And the last one is to send event to the state machine with notify state machine. So each of the events are the arrows, remember? And that will invoke the interpreter, move the state machine to another node, another state, and trigger the actions, all right? So what the developer needs to do is basically just draw the XML and just call these functions in code. So that creates an API in the database. And this is how we might look for writing new data in the database. So you have the customer tries to pay, and the gateway API will execute this function in SQL, for example, create Swish payment. Swish is a popular payment method in Sweden. And that function internally stored in the database looks like this. Create Swish payment. This is like pseudocode, so don't get hung up too much in the details. It just creates a state machine, it inserts into payments, and finally starts the state machine. Okay, so that's creating a payment, that's it. Internally, the interpreter of the state charts will actually move the state machine and trigger any actions that are needed, like the create job. So the payment processor, once it receives the payment, it notifies the payment gateway API. So we just confirm the Swish payment, which is actually this function. We find the machine ID for this payment, and we just notify that the payment was done. And that will trigger the audit job, notifying the merchant, and so on. Okay, so this is the synchronous API. This is the things that can live in the database. So how do we handle the asynchronicity, for example, the foreign state mutations? So this is how it goes. Remember this. We had the transaction 1 and 3. We solved this part with a state chart, but we still have the foreign state changes. So what do? Remember that we triggered 2 jobs here, store the charge job and the notification job. And this forms a pattern which is quite popular or very well known in microservices architecture called the transactional outbox pattern. The idea is that you never actually call an external service. What you do is you store in your database in a transaction and then have in a jobs table, and then have a relay do the actual job, okay? So it turns out that a database, in this case Postgres, is an excellent job queue. So the jobs are inserted into a jobs table in the database, and we use this API. We just enqueue, okay? Enqueue will just trigger this, basically just PG notify. So asynchronously notify clients listening to this job. The clients that are listening just need to call listen on a channel. And once they listen for it and they know they need a new job, they just call DQ. Okay? So that's how we get the jobs into the workers, and they can actually execute things like charge the customer, notify the merchant. And this is basically how we queue jobs. So in the state chart, we have a trigger action. When we enter a node on entry, we have a function called enqueue payment create job. And this is the function. It's a one-liner, right? The one-liner is perform jobqueue.enqueue, which is the API you saw in the previous slide. Or if we want to notify via webhook, we have also this job. When entering the paid state in the state chart, call the function notify merchant of payment update, which is also one-liner, which is basically our API for enqueuing. So it turns out that having logic in the database is quite simple. If you have the state chart and you have some hooks, you just need some one-liners to implement the specific details of the logic. So we talk about async, but how about concurrency? So you have multiple signals coming out from the world. For example, you can pay, but at the same time you can cancel the payment, but it also completed. The payment processor is telling you it's completed. How do we handle like all the different signals at the same time and have still a consistent data? And I'm going to give you an example of what may happen if you don't do this. You may be surprised that most companies that I've worked at, they don't think about transactions properly. This was a famous case of a bank called FlexCoin. They had Bitcoin, and they shut down after all of the Bitcoin was stolen. And then they published their postmortem, and it turned out that it was a race condition in their code. The race condition was that they were not using transactions properly. So they were vulnerable to a concurrency bug. And this happens to most companies that I've worked at. Like, developers don't think about transactions properly. They need to get familiar, we all need to get familiar with the isolation levels in the database. So in Postgres specifically, the default is read committed, which is vulnerable, as you can see, to 3 types of concurrency bugs. The only isolation level that is invulnerable to the 4 types none of race conditions is serializable. So let's talk about the serializable isolation level. It is a retry-based concurrency control mechanism, which is similar to software transactional memory. I'm not sure if you know software transactional memory. Maybe raise your hand if you do. It's kind of like a niche thing. It's famous in Haskell. It's probably one of the Enclosure too, and I think Scala as well. It's famous in the functional programming community. It's a way of having concurrency without thinking about it. You just put like a magic word, and then you have concurrency that is invulnerable to data races. And it guarantees that transactions execute one after the other, or as if one happened after the other, by just using the serializable keyword. It prevents all anomalies, and it doesn't require thought from the developer. Like, how cool is that? Like, every single company that I've worked at, they don't want to think about it. And this is a solution for it. Just use it. You don't need to think about it. So again, the downside is that it's retry-based. So if there is a problem, Postgres will let you know, hey, bad transaction, retry. And then you need to send the same queries for the same transaction. All right? So we have talked about how we implemented it, but how does it look like from the developer perspective? Like, it sounds like a crazy idea, code in the database. Who wants to code in the database and sounds crazy? So we had to go through a journey to actually get the cool tools and development workflow that we were happy with. So the first thing, or the top level thing, is that database should be treated as code. So we stored all of the code of our database in Git. It's versioned, is reviewed, is merged to master, and is deployed using CI. We use a tool called Sketch to manage deployments, but you can use anything that you like. And then the local development looks something like this. We just go to a file. I think I need to play this. There you go. You just go to a file, edit the specific function. We have some automation to run the test and deploy them locally using Docker. It's like any other language. Usually there are one-liners, so it's quite easy to just read and modify. And we have a custom CLI tool to create templates. Like, I want a new function, a new trigger, a new state chart, a new state chart hook, and so on. So testing, we usually use more end-to-end testing, Like, I'm a big believer in like full tests. But for unit testing, in the database, we use a framework called pgtab, which is just functions that look like this, and will give you assertions of the code, and you get everything happens in a transaction. It's quite fast. Like, we have hundreds of tests, and they run in less than a second. So for debugging, we use a tool called pgadmin4. You can have step debugging like any other language. I personally don't use step debugging. I've never used it in any other language. Haven't been able to get used to it. But I use pSQL as a REPL. I love REPLs. So for me, it's the best environment. Like, I just throw some queries, test my hypothesis, put it in a transaction, and then roll back, so I didn't affect anything in the database. And then one observation is that our code tends to be super simple. Like, there are no ifs, or barely none. There are no loops. There are no branching other than what exists in the state chart. So it's quite easy to follow. Like, most of it are one-liners, as I said before. And then it also has static analysis tools. Like, Postgres statically analyzes all the queries when you store them in a function. So it will tell you exactly what problems you have with a query, like variables that, or variables, no, like columns that doesn't exist, or clauses that are incorrect. If you use PL/PGSQL, the procedural language for Postgres, there's this extension called PL/PGSQL check that will give you even more tools, like dead code and bad returns, bad casting of one type to another, and so on. And then finally, we had to build some tools for observability and to measure performance of our code in the database. So the first tool that we built was we built some tracing in the database. Basically, every time we open a transaction, we call this function automatically, which is setting the local context. We set a request ID, which is generated by the API, and we store it in the local Postgres transaction memory. And we also store a trace context, which is actually the context from Datadog. So we can have some distributed tracing. So all the logs appear with this request ID and the trace context. And then when we look for example, the request ID across services, so we can see that the gateway got a request, and then it generated a job that executed in the worker. And remember that the intermediate step was storing the job in the database. So we have like the full journey of each step in the state chart, even if there are multiple retries in the worker, by just storing this information in the transaction context. And then we found that Datadog's database APM is fantastic. It gives you like really good insights into each function that is called in the database. We have like average latencies and P99 and how things have changed over time, which has helped us a lot to find bottlenecks that we have introduced in the past. We have a dashboard with the top 10 queries. This is what I see every day, seeing that we have no regressions, and I also see the volume of queries done to check that nothing is doing more than necessary. So finally, an anecdote of performance. This screenshot was taken last year around Black Friday. So we were just launching our payment gateway, so the traffic was just minimal. But you can see that before those two peaks that you see there, we have some traffic. The peaks are actually the weekend of Black Friday. You can see it's a lot more traffic. I'm going to show you the CPU for the database that week. Can you spot Black Friday? You can barely see 2 bumps that day. That doesn't amount to 0.5% of CPU. All right, but that was with minimal traffic. So 1 year later, we're handling almost 60% of all transactions at Boozt. So you can see there is an order of magnitude more queries going to the database. Can you guess how much CPU we're using? Well, surprise, we're using exactly the same. It's a bit more spiky, unfortunately, because I enabled something from Datadog that pulls some data periodically, so you see those spikes, but you can see that it's also around 6%. So we can handle an order of magnitude more queries than before with the same CPU, which is kind of surprising because one of the first things that you read on the internet when you type like, can I have logic in my database? The first counter argument is like, the CPU is going to explode. You will not be able to handle all the queries. You will not be able to scale. Okay, so we're almost done with our journey. An entire payment gateway in a database. So I think the title was a bit inflammatory because if you look at our volume of code, all the code of SQL and PGSQL is only 20% of what we do. The rest is actually interacting with external systems. So it's not all of it. But I would say that our core business logic is actually in the database. So with that, I leave you with some time for questions. And thank you for attending.
Thank you so very much, Jose, for sharing that. That's very, very cool. So we're going to use the catch mic for Q&A. So just as you get it, make sure you speak into the microphone. It's not overly sensitive. And so I'd like to see if anybody has any questions before we...
So my name is Shivram, working from Cognizant on the payment gateway. I lead the payment gateway solutions across multiple banks and customers. This is very interesting from a point where you are developing a whole solution on a DB side. So but I have some specific questions on how are you managing the performance elements of it? How are you managing the tokenizations elements of it? How are you managing them, or you're giving it away to a freedom pay or any of the gateway solutions? How are you? Are you able to do it? Because I'm very keen, because if you're having an answer, then I will want to work with you more. That's precisely the direction which I'm going towards.
I'm not sure I understood all of it because there's echo, like the other presenter said. But I will rephrase the question and let me know if I understood. The question is, one, how are we managing performance?
One is performance. The other is the tokenizations. So
localization.
Yeah. From a gateway model, if you want to maintain the tokens, how are you generating the tokens in the form that you generally use?
Oh, tokenization.
Yeah.
We're not handling data like credit card payments directly ourselves yet. The plan for us is that we will also have this database idea, but in an external environment, like we will separate entirely in another database. And what the system will do is that it will get the credit card, communicate to this other database system, tokenize there, and the non-PCI compliant system will use this other as a proxy, which is the same idea in most services that you see. So that's for tokenization. The question about performance, we've built a lot of like observability tools, as you saw, around the database. Datadog has been amazing with this. I have some ideas for scaling if things go bad with this. What I'm surprised, as you saw in this CPU graph, that's not something I was expecting to see, is that we could handle an order of magnitude more with the same hardware, same thing, everything is the same. So I'm really confident that we can handle like 2 orders of magnitude more with the same hardware. If we ever need to scale, then my plan from the beginning was sharding. So to have shards like different databases for bigger customers, for example. So my plan in the beginning was to use a product called Citus, which is a transparent like proxy, let's call it, that will shard the Postgres database and route your queries appropriately.
Thank you. Thank you.
Yeah. One question is you mentioned that your logic put in the database. What's the advantage with if I put in the controller microservice? Maybe that's a regular way. And what's the advantage on the compare you select to put logic in the database?
So the question, So if I can rephrase this, is what's the difference or the advantage with a microservice architecture?
Yeah.
Okay, good question, because I started with also this idea. I'm going to start responding to this from two perspectives. The first is that, from my perspective, microservices are a solution for team structure. And from the beginning, I decided to structure my team as a small team, okay, a full stack developer. So microservices, if they become a thing for our team later, or our teams later, would be if I need to split the teams into their own units. But on the other hand, if you remember the slides about complexity, what I discovered, one of the insights is that the more foreign state mutation changes that I have, that is, the more HTTP requests that I have, the more work that I need to do. Retries, more state changes, taking care that the transactions can be rolled back. So it's a lot more work. So this solution enables the team to basically just draw the system in a state chart, implement the hooks, and that's it. You can ship it to production. There's no need to deploy multiple services, instrument multiple services, do the rollbacks because the transaction needs to be distributed and so on. I think the main advantage is simplicity, and with note of the disadvantages so far, I think that we can easily scale 2 orders of magnitude or 3 orders of magnitude more with the same architecture.
Okay, thank you. One more question. Maybe I've missed that part. So DB, you use the SQL DB or non-SQL? For the SQL for transaction control, but for non-SQL, we can easily to scale up. So what's that part? I mean, I probably missed that part, but
I couldn't understand the question. Can you repeat?
You talked about the database. Which kind of database? Is non-SQL, SQL?
Oh, it's PostgreSQL.
Okay.
Yeah.
So your state machines are pretty simple, and I think that's like part of the elegant design. Are there any error handling cases where the state machines have to handle error cases?
Yeah.
And how do you handle that?
Yeah, that's a good question. One of the amazing things that I have discovered with statecharts is that when you start drawing them, it immediately starts prompting questions from the team, like, what happens if this fails, right? So you start drawing arrows, like, okay, from this state I can go to error. And then you start asking, like, how can I recover from the error? Like, what happens if there is a discrepancy between the payment processors and what we have? So you draw an arrow back to a retry, for example. So there is, I would say that a lot of the complexity in our state chart, I showed a simple one, is actually this error handling. Like, what happens if something goes back and how can we recover from this? And there's been a lot of learnings. Like, the first state chart that we created, there were like simple error cases. And then as the reality hit, it's like, okay, it's a lot more complex, like the retry flow and the discrepancies that we can have with a foreign state.
Another question would be for the composite state machines. So if I wanted to replay an entire composite state machine, how would you guys rebuild that state from the original event? It's like in an original queue, you would just refire the original job. All the processes would start processing and happening, but how do you do that with composite state machines and a transactional database?
So the question is, how do I requeue a job here? Okay, we have some functions called like retry something something, and then retry something something is, if I am in this state, like error state, go back to the state of check again. So we basically just send a signal to the state machine that will go back to this state, which will trigger a new job, and so on. That can be done infinitely. Like, you can have as many retries as you like.
Sorry, last question. Do you find it hard for other developers to transition from like an OOP kind of framework thinking to this DSL within these state machines inside your own kind of custom query language?
Yeah, I would say this is one of the biggest things about this is that you have a lot of skepticism about everything. It's like, how will this work? Like, this sounds like crazy. But the developers that I have now, my team, they're pretty much sold on the idea. Like, they love it. Like, they're like amazed. Like, wow, I never knew that you could do this with Postgres. I never knew it could be so simple. Like, once you discover that if you restrict yourself, like you use more restrictive systems, like you have more creativity in a way. Like, I'm not sure if you have experienced that. Like, if you have like all the possibilities in the world, you have no way, like, should I go this way or this way? But if you restrict choice and you say like, this is the only possible thing to do, people get a lot more creative and more productive.
Thank you.
Yeah.
Awesome. I know we didn't get to all the questions. Unfortunately, we are going to have to end the session now, but we do appreciate that. I think maybe if Jose is available, we can try to corner him here for a minute or two on the side. But thank you all, and we'll see you at the next session.